Beaming internet from the middle of the woods using an extra-large pizza-sized satellite dish placed on top of your house up to a satellite orbiting 550 kilometers above Earth's atmosphere is, let's be honest, technologically mind-blowing. What's even crazier is that the Starlink satellites move incredibly fast, around 27,000 kilometers per hour, and yet data is being sent back and forth between them and your dish at hundreds of megabits per second. All this happens while both the satellite and the dish are constantly steering the beam between them. And since each satellite quickly moves out of view, the dish must switch to a new satellite about every 4 minutes. If that sounds impossible, stick around. In this video, we'll break down how Starlink internet works, from the inside of the dish to the data beaming through space. We'll explore 3 key sections: how the dish generates a beam powerful enough to reach space, how the dish steers that beam to follow fast-moving satellites, how data is encoded and sent, allowing you to stream multiple HD videos from the forest. The difference between TV dishes and Starlink. TV satellite dishes only receive broadcast signals from satellites located 35,000 kilometers above Earth. They don't send data, just receive it. And those signals are wide, covering whole continents. Starlink is different. It sends and receives data from satellites that orbit much lower, just 550 kilometers up. That's about 60 times closer than a TV satellite. This shorter distance means much lower latency, around 20 milliseconds, which is crucial for online gaming and browsing. However, because these satellites are closer, they can only cover a small region. To provide global coverage, Starlink uses over 10,000 satellites in fast-moving low Earth orbit. What's inside the Starlink dish? Dishy McFlatface. Dishy has motors used only for initial alignment. After setup, the motors don't move the dish anymore. Opening it up, you'll find a structural aluminum plate, a large printed circuit board, PCB, 640 small microchips and 20 larger ones, a GPS module, and a main CPU. On the front side, you'll see a grid of about 1,280 small copper antennas arranged in a hexagonal pattern. Each antenna is controlled by the microchips on the board and works together as part of a phased array. How a single antenna works. Aperture-coupled patch antenna. Each antenna is about 1 centimeter across and composed of 6 layers inside the PCB. At the bottom, a copper wire, microstrip, carries a 12 gigahertz signal, switching polarity every 83 picoseconds. This high-frequency signal doesn't behave like household electricity. Instead, it causes electric fields to form and flip back and forth in the copper patch above. As the voltage oscillates, it creates electric and magnetic fields that form electromagnetic waves. These waves travel outward in a spherical shell, kind of like a glowing light bulb in space. To make this signal strong enough to reach space, we use beamforming. Beamforming, combining 1,280 antennas. One antenna isn't powerful enough, but if you synchronize all 1,280 antennas, their electromagnetic waves interfere constructively in one direction, amplifying the signal like a laser beam. This focused signal is powerful enough to reach satellites in orbit. It's not just 1,280 times stronger. Due to constructive interference and directionality, the gain is closer to 3,500 times. The beam must follow a satellite moving at 27,000 kilometers per hour. Mechanical motors can't steer fast enough. So Dishy uses phased array beam steering. Here's how it works. Each antenna transmits the same signal, but slightly delayed, phase shifted from the others. By adjusting the phase, the direction of the beam changes. Delay the signal, beam angles left. Advance the signal, beam angles right. Using this technique, Dishy can steer its beam in any direction within a 100-degree cone without moving physically. GPS data and satellite orbital data tell the software where to point. The software calculates phase shifts and sends them to 20 beamformer chips, each controlling 64 antennas. These adjustments happen every few microseconds. How data is encoded. 64 QAM modulation. Now we understand how the beam is formed and directed. But how does Dishy actually send your Netflix stream? It uses a method called 64 QAM, quadrature amplitude modulation, where amplitude equals signal strength, Phase equals signal angle. Each combination of amplitude and phase represents 6 bits of data. There are 64 possible combinations, 6, each one called a symbol. A new symbol is sent every 10 nanoseconds. Because the base frequency is 12 gigahertz, each symbol contains about 120 wave cycles. That gives us around 90 million symbols per second, or 540 million bits per second. Dishy can't transmit and receive at the same time, so time is split. Around 74 milliseconds per second for upload and 926 milliseconds for download. These are interleaved to reduce latency. Once the binary data arrives, your device decodes it using video codecs like H.264. Real electromagnetic waves are just 2.5 centimeters apart. Dishy is 55 centimeters wide. 22 million wave cycles fit in the space between Dishy and the satellite. Most of the time, Dishy is in receive mode. The physics of receiving is just the reverse of transmitting, but otherwise the same. Starlink satellites have 4 phased arrays on board, 2 for Dishy users, 2 for ground stations, and yes, the same technology allows for mid-flight airplane Wi-Fi. Starlink and Dishy McFlatface represent a marvel of modern engineering. A blend of advanced physics, electronics, signal processing, and orbital mechanics. To master technologies like this, you need a multidisciplinary mindset. Thanks for following along. If you want to learn more about video compression, electromagnetic waves, or space technology, keep exploring.